Find the area under the function on the given interval using the limit definition. Here's the function f of x equals 3x squared minus 5x minus 2 on the interval 0 to 2. So we have this limit here. This is what the limit definition is when you're trying to find the area under a function. So the first step, I'm going to break this down into 4 steps. The first step is to find f of a plus b minus a over n I. So in order to do that, you need to know some information like what a and b are. And it turns out over here, the interval, these are your a and b values. So this function changes into this. And when we simplify this down a little bit, you'll see that this equals this. So that's fine. We've now simplified what is inside the argument of the function. But what does this mean, this entire thing? Well, we've got to go back and look at the actual function and substitute 2 over ni in for x here and here, and then simplify that down as much as you can. When you substitute it into the function, it looks like this. 3 times 2 over ni squared minus 5 times 2 over ni minus 2. Now our goal is to simplify this expression as best we can. So the first thing to do is to square the term here and then multiply it by 3. And when you do that, 2 squared is 4 times 3 is 12 over n squared I squared. The next term, negative 5 times 2 is negative 10. So that's minus 10 over ni. And then the last term is minus 2. That's the best we can do for right now. On to step 2. Step 2 is to find b minus a over n. And from the interval on the previous page, b is 2 and a is 0. So this whole expression here turns into 2 minus 0, which is 2, all over n. And one thing I want to mention here, I should have done it on the first page, is anywhere you see an n or an I, it just stays n or I. You will not put any numbers in for n or I when you're using the limit definition to find the area underneath a function. Next, the third step is to find the summation of all of these things. And this was what was computed in step 1, and this was computed right above in step 2. So now we're going to find the summation of all of this stuff. So the sum as I goes from 1 to n of all of this. And since there is the product of two different expressions inside of this sum, we must distribute this 2 over n to all 3 terms of the first expression. And when you do that, that'll look something like the sum as I goes from 1 to n of 24 over n cubed I squared minus 20 over n squared I minus 4 over n. So now we use the sum and difference rules as well as the constant multiple rule to separate these 3 terms into 3 different sums. And when you do that, make sure to remember that constants can be pulled out of a sum, common factored out of a sum to the front, and n is a constant. So when we separate this all out, it'll look something like this. So now that it's all separated out with the constants pulled to the front, and the i's are the only thing that are left in these, and for whatever reason I leave this constant in here because I know the next step will be to just multiply this by n. So the next step is to use the formulas for the sums of i's and the sum of a constant. And when you do that, you'll get something like this. This will be 24 over n cubed. And the sum of I squared as I goes from 1 to n, from our formula, it looks like this. N times n plus 1 times 2n plus 1 all over 6. So that's that first sum. I'm going to do this next sum in red. So we'll be subtracting the sum of 20 over n squared, and the sum of I is, as I goes from 1 to n, is n times n plus 1 all over 2. And this last term I'm going to write out in blue, and that just ends up being the constant times the upper bound. So that'll leave you with a 4. And the signs in between these are both subtraction signs. They are right here. They come along for the ride. So now the last thing I want to do is within each term. So I'm going to start with the first term, and I'm going to simplify any constants that I see. So I know 24 is here and 6 is here. I can reduce those. 24 over 6 is the same thing as 4. So I know I will have a coefficient of 4 in the numerator, and also I'm going to see if I can cancel any n factors. So there's an n here, and I know there's an n in the numerator, so I can cancel one of those away. That'll leave me with an n squared in the bottom, and in the top there is still an n plus 1 times a 2n plus 1. Minus. In the second term, again, I want to see if I can reduce these constants, and yes, I sure can. That leaves you with a 10 in the numerator. And then again, I want to look at just the n. There's an n squared in the bottom and an n in the numerator. So I know I can cancel one of those, and it'll be left with an n in the denominator. And you're left with an n plus 1 in the top. And the last term, you cannot simplify it any more than it already is. It's just minus 4. So this takes us to the last step. Finally, step 4. Find the limit as n goes to infinity of the answer found in step 3. All right, so this means we are trying to find this. And as it turns out, you can find the limit of each term and combine them accordingly. So I'm going to find the limit of the first term first. So the limit as n approaches infinity of 4 times n plus 1 times 2n plus 1 all over n squared. What happens here is you can FOIL out these two binomials and then multiply everything by 4. So when you FOIL it out, you get something like this in the numerator. And the next step is to find out what this limit equals. And if you recall, a long time ago you learned something, you learned the method on how to find the limit as n goes to infinity. And that is, if you divide every term by the highest power of x in the denominator, so you divide each term by n squared, you'll get a limit that looks something like this. And with this limit, you know that as n goes to infinity, this term and this term, because there are n's in the denominator, will both go to 0. And what you have left is the limit as n goes to infinity of 8 over 1. And that leaves you with a limit for that term equaling 8. And if you do this for the other two terms, you'll see that this second term has a limit of 10. So I'll just write here limit as n approaches infinity of the second term equals 10, and the limit as n approaches infinity of the third term is 4. So putting these back in the correct order, this is the limit of the first term, so we will have down here in red 8. And then you subtract the limit of the second term, so that is minus 10. And then you subtract again the limit of the last term, which is 4, so minus 4. This gives you a total area of -6 square units. With that last answer being -6, you might be wondering, how the heck is there a negative area? My whole life I've been told there's no such thing as negative distance, there's no such thing as negative speed, there's no such thing as negative area, no such thing as negative volume. Well, math just sort of blew your mind. Let's take a look at what a graph of this thing looks like. A rough graph of this function f of x equals 3x squared minus 5x minus 2 is in blue over here on the right. One thing that you need to understand, first of all, is that when we are trying to find this area, we're trying to find the area between the function and the x-axis. And we have to specify a starting x value and an ending x value. Otherwise, the areas get really large really fast. So the region we are trying to encompass here, we know over here on the left the function is this, but that only exists on the interval from 0 to 2. So I'm going to highlight it for you. We're checking the area between the function and the x-axis between x equals 0 and x equals 2. So we're trying to find this shaded region right in here. And one thing to note is that this shaded region is 100% underneath the x-axis. It's kind of hard to see the laser pointer there, but it's 100% underneath the x-axis. And whenever you have an area that is under the x-axis, this will be a negative area. So, mind blown, there's now such a thing as negative area in mathematics, and it only happens when you have an area that is underneath the x-axis.